Hey, good evening, doctor. This is Group SW-ML-26, and we are presenting our project about Babesiosis detection in cattle or in animals. So these are my team members: Ariko Joel, Kamandatha, and then Ngarang John. Here's the quantitative table that we're going to talk about in our presentation. So I will start with the background and then introduction. So background, with the background, traditionally, automated parasitological detection relies on two things: heuristic pixel differencing and morphological thresholding. Heuristic pixel differencing, uh, here veterinary doctors use it to compare the color and brightness of the pixels, and then the to find out the different areas that might be infected with the parasite. Then for morphological thresholding, these were the rules that were set based on the shape and size. For example, if something was found round and dark, then it could be a parasite. So these critical methods are computationally cheap, and they suffer from catastrophic false positive rates. And these were resulting into poor performance, cause anemia, reduced medical production, weight loss, high mortality, and then also death. So babesiosis sometimes is confused with the malaria plasmodium when they are viewed under the microscope, since both of them have a round ring inside. So in our introduction, we shall talk about the manual microscopy diagnosis of the GIMSA stained smear blood images. These are the images that we're going to look at, which result which was resulting into subject into slow, and then it was also error prone. So we are basically talking about babesiosis, and it is a parasite disease in animals that requires timely and actual detection for effective treatment. We shall be using the deep learning, and basically we shall be using the CNN, which is good for image analysis, so that we detect parasites in the blood smear images. This approach has our goal is to have a faster, accurate, and scalable veterinary diagnosis. Here are some of the recent trends. The deep learning is transforming medical image analysis by providing fast and more reliable diagnosis compared to traditional methods. We have a faster transfer rate that enables accurate and limited medical data, making it an ideal for veterinary applications. We have AI assisted systems that now successfully detect parasites from the GIM sustained blood smear images. We have the mobile and then the cloud-based tools that help the rural veterinary doctors in getting their results. We have unexplainable AI techniques that are improving trust and transparency within our clinical decision making. So here's our problem statement. It is categorized into domain application and then computational application. So for the domain application, we're talking about the real world problem under a specific field that our system is currently solving. And for this case, our domain is veterinary, and our application problem is that we're detecting babesiosis in animals. So the manual blood smear examination is slow and subjective, resulting to delay in the day treatment in the rural areas. Uh, Babesiosis is frequently confused with the plasmodium rings. We have other co-infections like Theileria and Plasma and other pathogens that are common in personal systems that worsen the clinical outcomes. So that's all about our domain application. And then our computational application, for it is looking at the computational challenges that we are solving, the specific difficulties that the model must outcome, and also our goal is to ensure that our machine learning system solves our problems. So basically, we need to develop an accurate multi-class classifier to distinguish between the Babesia parasites from other similar parasites. For example, a Plasmodium, the leukocytes, and then the white blood cells which are healthy. Then we also need to address severe class imbalance where our Babesia infected cells were being represented by 10% of the data set compared to healthy ones. So we need to enable the reliable real-time detection of Babesia from the microscopic blood images under varying staining conditions. So here are our research questions and the objectives that we came up with. So the research questions, these are the questions that we have. So basically, let's ask ourselves: can we transfer the learning of the public parasites to detect babesiosis with the veterinary grade ashes? How? Then also the second question: How well can the model distinguish Babesia from other similar parasites? Then now, these are objectives to prepare and explore a relevant subset of microscopic blood smear images, develop and train a deep learning classifier for Babesia detection, then also to evaluate the model performance using the standard metrics and confusion analysis, then also to demonstrate a prototype interference tool for the new images. That is our graduate that is working on it, supervises the interface for detecting babesiosis. So these are the research contributions and outputs that we come up with. We developed a focused multi-class babesia detector using our base trained model, which was efficient before on a public data sets. So we built a robust negative set whereby we combine the healthy red blood cells so that we can reduce the false positives. So we achieved the promising H rates of 9 and above in all the models that we trained, the H rates in the models that trained between the Babesia and the non-Babesia classification. So we designed and deployed a user-friendly interface that supports the practical use in the veterinary clinics. And below is the link that will take you to our Hugging Face where the model was deployed, where it is ready for production. So this is the methodology and the system architecture. Initially, we first identified the problem, and then we analyzed it. We collect our data sets for pre-processing, built the model, we trained the model, we validated it, we tested it, and then packaged it for deployment. So this is the model that we used, and this is its architecture. We used the efficient net before, and it was basically running based on the following principles. First of all, we used to have the image input whereby the user uploaded the image, the system convolution. Then you have the mobile inverted convolutions, which were composed of different layers, and each layer had its own role that was playing during the analysis. Then after, we have the fully connected classes and also the output. The output was consisting of the classes and their score, their probability scores. So our data set and the description analysis, we got our data set of the game sustained blood physical peripheral blood smear images from Mendel. Then also our class was divided into four classes. Our data set was divided into four classes: the Babesia, Plasmodia, the red blood cells, and then the leukocyte. Our images were format JPEG, PNG, and they are on the blood in their structure as you uploaded it, and the all game sustained 10 blood smear images. So our EDA insights, the first insights, we had some severe class imbalances, uh, high visual high visual similarity between Babesia and Plasmodia formerings, the variation in the image size, and also staining intensity. I'll hand over to my next colleague to take over.
Okay. All right. Thank you for presenting. Okay. Is that where it's starting from?
Yeah, you can start from there.
All right. Uh, Thanks for presenting. Uh, so let me take over through from the EDA. So here, these are the exploratory that we made through our data sets. As briefly, formally, explained the description of our data set. So here, we had to first, okay, let me start. We started by checking the class distribution, where we saw that the red blood cells had the most number of samples compared to the others. Then for the imbalance ratio, Plasmodium was heavily affected. That's why you're seeing it has a high ratio as compared to others. Then, okay, for the interest of time, I may not be able to explain all of them. Still, under the class distribution, I talked about it. The class balance, we saw Plasmodium was the highly affected. Then the image dimension distribution by classes. Images, they have different length and width, height, and so on. So therefore, we had to explore in that it helps us to come up with a resolution that we can feed into our model and it will help us make concrete solutions after the training. Then we had the ratio, aspect ratio, distribution aspect here, and also the variation of the width versus height. All these aspects we had to explore so that we can come up with a strong pipeline with a few or not at all outliers. Then also the file size distribution by class, we had to check on this. It's okay, I think, yeah. Then no, yeah, there. We had to check the metadata. Next slide, I mean, that one. Well, we had also to check the metadata feature correlation heat map. This one gives us a we can remove some or some features or leave some features or leave remove or add actually in order to see that our model does not do overfitting or underfitting. Then we had temperature scaling and so on. It's okay. We had model architecture comparison. So here basically we had to check on which architecture we may give us results based on accuracy, speed, and efficiency. So most of these architectures you've seen here, me and my colleagues have used them in training the models, the 4 models each, and we had evaluation results as they are written in the write-up or the IEA document. Then for the explainable AI analysis, of course, we used the breadcrumb heat maps as you saw previously. We used to visualize. We use these heat maps to visualize the regions the model focuses on when making predictions. So here we used the confusion matrix whereby we saw, anyway, my colleague will explain those results, but of course, it's one of the explainable AI aspects whereby we visualize these results using the confusion matrix. Then the model successfully highlights Babesia parasite roams and also other structures in the main decision areas, meaning it used the main diagonal. Many of the cells were predicted via the main diagonal of the confusion matrix show. Hence, it was showing that the model was perfectly doing well. Then, in most correct predictions, the model concentrates on the parasitic morphology rather than, of course, the background stainings. Then it revealed that the breadcrumb revealed that similar structure of plasmodium, the heavy stains, artifacts, and the overlapping cells. Next slide.
Oh, thank you.
I think my colleague will take over from here as he will explain these results and so on.
Okay.
Thank you.
Thank you. Thank you for that explanation. I'll be thinking through the results we got from training the model, our best model, with that is EfficientNet before. Yeah, so the first one, we have the loss and the accuracy for both the training loss and the validation loss. Then for the accuracy, we have the training accuracy and the validation accuracy. So for the loss, as we can see here, for the training loss at first, for the first approach, it was at 0.24. Then for the second one, it started reducing. It came to 0.1, like that, until we reached to 0.02. Yeah. Then for the validation loss, for it was stable. It started from 0.6. Then it went up up to 0.7. Then it came down for 8.5. Then started rises, pause, and then got a steady curve here from average 12 to 15. Then for the accuracy, for the training accuracy, at first it was very low for 8.1. Then 8.2, the accuracy went to 96.5%. Then for 3, 4, 5, it started increasing until it reached 99.7. Yes. So for the validation, when you try to validate what we are trained, the accuracy was at 98.9 for the first epoch, then 98.9 still for the second epoch, like that for 3 and 4. Then it went up for epoch 5, it was at 99.5. Then it went down again for epoch 6, 8, like, yeah. Then it was decreasing, increasing, but it was in 99. So it didn't go below 99%. First go back. So the confusion matrix, as you can see, there was a lot of confusion. The only confusion that was there was between the RBC and the plasmodia. Yeah. Then for the test reports, our accuracy, our precision recall for Babesia is 1 for the leukocyte, plasmodia is 98, and RBC is 99, 0.99. The F1 score is 1, as you can see. Then the accuracy was at 99% for the best model. Next, please. Yeah, model selection and deployment. So we selected the efficient net before because it had the highest accuracy for the training. And also, why we chose this model, it has high accuracy. Yeah, it proved strong performance on medical images. Then efficient scaling, using compound scaling, that is depth, width, resolution for better feature extraction. So when you try to do scaling with this model, it performed very well. Then optimize performance, it balances accuracy and computational cost. For the computational cost, we mean the loss and uh, we mean the loss. Scientific justification, it captures fine-grained features in this gizmo stained microscope images. Yeah, so when you are working with this with this model, for it captures fine-tuned features in the stained microscopic images. So as you can see for Babesia, when you look at it, it is similar to other parasites, the microscopic images. So when you use this model, it can clearly capture the features of Babesia and relate them to other parasites that may be similar to it, but then for it can generate it very well so that you can know that this is Babesia and this is not Babesia. It is suitable for small and complex visual patterns, parasites in blood cells. Yeah. So when we are training the model, that's why it goes up to 99% training accuracy. Transfer learning improves performance with limited data sets. So when you use EvisionNet before for transfer learning, the performance is increased. As you can see, it was at 99%. So the deployment, what we did to deploy our model, we first trained the model, then we saved it, then we created a gradual app using Hanging Fest. Yeah, so it's like a web application where you just inserting your picture and training the model to predict whether it is Babesia or not. Then we push the repository. Then we went to Hanging Fest and deployed it. Then everyone, it's now accessible to anyone. The link was provided earlier. That picture, there's the user layer where doctors and lab technicians upload the Microsoft images. Then the presentation layer, it is the front end, which is the gradual UI, where you can upload and view the results. The application layer, the backend, we have the image pre-processing module, the efficient and before module, then the prediction logic. So the logic predicts whether it is Babesia or not. Then deployment and hosting, we use Hanging Face still spaces to host using cloud. Yeah, next. Yeah, demonstration of the debug product. So if you are to use this model or this where we deployed it, you input in an image of a gizmo blood smear image that can be either Babesia or leukocyte or RBC into the model, then you get the results. How it works, The user uploads the image via the gradual interface. Model analyzes image for Babesia. System returns prediction plus confidence scores. The output, positive or negative detection, instant web-based results. Yeah, from Hanging Face, as you can see down here. So here, when you click on upload the image, it takes the image into the backend. Then the prediction occurs and you get the results. The core IP components, we have the trained mode ML model for Babesia detection, saturated and labeled microscopic datasets, image processing and classification pipeline. Innovation value is we have automated disease detection in veterinary diagnosis, reduced reliance on manual microscopic analysis. So instead of taking time looking into the microscope to check if there's a Babesia or not, here we just inputting the image of the microscopic image into our application. Next. Yeah, conclusion and limitations. Conclusions, we developed an automated babesiosis detection system using efficient than before. Yeah, this is what we have deployed. The accuracy we got 99% and fast image-based diagnosis from microscopy images. So the accuracy, as we saw before, it was 99%. Then you can just upload very fast, like within 5 seconds, you can get the results back after uploading. We implemented a user-friendly interface using Gradual, successfully deployed on Hanging Face spaces for real-time access. So anyone can access this one at any time. Demonstrates the potential of AI in veterinary diagnosis. So this can be helpful in the veterinary diagnosis for babesiosis or any other disease that we can include in this in the future. The limitations, the model accuracy depends on data set quality and size. So the accuracy actually depends on what we have in our data set. Doesn't depend on the quality of our images is so high. That means that our accuracy is, that's why our accuracy is not high. But if you have like low quality images, it will be hard for us to get this accuracy. It is limited to JSMA stained Microsoft images only. Yes, not fully validated for clinical stock real-world deployment. Performance may vary with poor image quality, limited scalability on Hanging Faces, prototype deployment. Yeah, this is because it is not yet fully paid for, so that's why it's like that. So these are some of the references we used. As you can see, Alvarez, JA. Acknowledgement would like to acknowledge Dr. Gadiwango for the guidance and support. Makerere University for giving us this opportunity to be here. Courses, of course, for the course they are provided to us, the resources and the environment, mainly data set. Mainly it's where we got the data from, the data set we are using. Then team members and the family for the collaboration and encouragement. I think that's it from us. Thank you for listening.